Now let us look at example 2. We have a tank that initially contains 45 kilograms of liquid water at 45 degrees centigrade. Liquid water enters at 45 degrees centigrade with a mass flow rate of 270 kilograms per hour. A cooling coil removes energy from the water at a rate of 7.6 kilowatts. A paddle is used to mix the water such that our temperature can be assumed uniform throughout, but through viscous dissipation, we introduce 0.6 kilowatts of energy. We want to determine the variation temperature with respect to time. Schematically, we can show the system. M.1 is our water entering at a flow rate of 270 kilograms per hour with a temperature of 45 degrees centigrade. M.2 is the mass flow rate of our water exiting, now with a different temperature. We have our cooling coil, where we have a mass flow rate of coolant entering that is then removing energy from our water. Additionally, our paddle wheel spins, adding energy into our system. To determine the variation temperature with respect to time, we're going to have to apply the conservation of energy equation. To begin, our non-steady conservation of energy equation becomes dEdt is equal to Q dot minus W dot plus M dot times the respective enthalpy, kinetic and potential energy, less M dot times our respective enthalpy, kinetic and potential energies. M.1 and M.2 are going to be one and the same. Now, if we ignored the change of our kinetic and potential energies and we just call M.1 and M.2 M dot, we can say that now our time rate of change of energy within our system is merely the time rate of change of internal energy within our control volume, which is equal to the rate at which heat is supplied, less the rate at which work is done, plus our mass flow rate times the difference of our enthalpy entering and exiting our system. Now, internal energy is what you have to solve for. We want to determine the variation of our internal energy of our system with respect to time. And to do such, we recall our internal energy is equal to mass within our control volume times our specific internal energy. If we differentiate this quantity with respect to time, we'd have the mass in our control volume times the time rate of change of our specific internal energy, which would comprise the left-hand side of our non-steady conservation of energy equation. Since we're interested in the evolution with respect to time, we can employ the chain rule to re-express our time rate of change of specific energy. dUdt would be equal to the derivative of our specific internal energy with respect to temperature times the derivative of temperature with respect to time. In doing such, we recognize that dUdt within our system would simply be the definition of our specific heat. Thus, we can express the time rate of change of our specific internal energy as our specific heat times the time rate of change of temperature. Thus, the time rate of change of the total internal energy within our control volume is simply equal to mass of our control volume times the specific heat of our fluid times the time rate of change of temperature. On the right-hand side, we have to recall that our enthalpy is equal to our specific internal energy plus our pressure times our specific volume. In doing such, the difference of our enthalpies between state 1 and state 2 becomes U1 less U2 plus nu1 P1 minus nu2 P2. Since our pressures are the same and our specific volumes aren't going to vary drastically with respect to temperature, we can say that the difference of our enthalpies will merely be the difference of our internal energies. And the difference of our internal energies is merely our specific heat times our change of temperature, where T2 is going to be expressed as T, the temperature of our outlet fluid. T1 is the temperature of our fluid entering our system, which is a fixed 45 degrees centigrade. Thus, H1 less H2 is equal to C times the quantity T1 less T. Thus, our conservation of energy equation becomes the mass within our control volume times our specific heat times the time rate of change of temperature is equal to Q dot minus W dot plus M dot C times the quantity T1 less T. And what we want to do is solve for T. Thus, if we re-express this in terms of our highest derivative, we have the time rate of change of our temperature within our system plus M dot per mCv times T is equal to a constant. This right-hand side, which is expressed as Q dot minus W dot per mCvc plus M dot per mCv times T1 is a constant value. These properties do not vary with respect to time. If we call the second term within our previous equation A and the right-hand side B, we have the following. Our time rate of change of temperature plus A times our temperature is equal to B. This is a first order linear differential equation, and we can solve this via various methods. What we will do is sum our homogeneous and particular solutions. To determine our homogeneous solution, we set the right-hand side equal to 0. That is, we have the time rate of change of temperature plus A times the temperature is equal to 0. Or we have the time rate of change of our temperature is equal to minus AT. Or we have 1 per T, the time rate of change of temperature is equal to minus A. Or, grouping like terms, we have 1 per T dt is equal to minus A dt. Thus, if we integrate, we have the natural log of t is equal to minus A t plus c, where c is a constant of integration. Thus, if we solve for t by exponentiating, we have our temperature as a function of time is equal to e to minus at times e to c, where e to c is just a constant c. Therefore, our temperature as a function of time is equal to c e to minus at. Now this is our homogeneous solution. This has to be summed with our particular solution. The particular solution is found by setting the time rate of change of temperature to 0. That is, we'd have at is equal to b. Or this is saying that we are going to assume the response of our system takes the form of our right-hand side. Or that is, our temperature as a function of time is going to be b per a. Summing the homogeneous and particular solutions, our temperature as a function of time is equal to c e to minus at plus b per a. Now, in terms of our system variables, we have our temperature as a function of time is equal to c e to the minus m dot per mcvt plus q dot minus w dot per mcvc plus m dot per mcv t1 times the quantity mcv per m dot. Now we still have a constant of integration that we have to solve for, c. And to do such, we're going to apply our initial condition. When t is equal to 0, our temperature within our system is equal to T1, i.e. 45 degrees centigrade. Thus, e to the 0 is going to be unity. Thus, we have c plus the quantity q dot minus w dot per mcvc plus m dot per mcv T1 times the quantity mcv per m dot is equal to T1. Or c is equal to minus the quantity q dot minus w dot per m dot c. Thus, the solution takes the final form. T of t is equal to T1 plus q dot minus w dot per m dot c times the quantity 1 minus e to the minus m dot per mcv t. What we notice is our temperature is going to change exponentially. That is, we have a constant value, and our temperature is going to decrease as we remove heat. Now this is going to tend to a steady state value as time tends to infinity.